Here is the question that I answered the previous part of this video with, and largely this is about interpreting this equation, where you have to now realize that the 5 Newton force has a force displacement vector of 5 meters to the right, and the 2 Newton force has a force displacement vector of 4 meters to the right. And so when you do that and recognize that the x component of that 2 Newton force is negative 2 newtons, then we come up with 17 joules. Well, now we have some tools to deal with more complicated situations, and one situation we must deal with is friction, because it's so common and so important. So it causes conversion of mechanical energy in our system into thermal energy, and we would really like to be able to calculate how much. But we can't treat friction as an external force and get the work due to it. We talked about why in the last lecture. So what we can do is define an isolated system, such as a block sliding across a surface, and include the surface, and so now the change in kinetic energy of the system is just the negative of the change in thermal energy. But I'm going to be very picky about how I define this system. I'm going to include only the thinnest of thin layers of the surface, just enough that the thermal energy is in it, but I don't have to think of its inertia. And I'm going to think of the block as rigid. And so now, because I can ignore the inertia of the surface, the displacement of the center of mass of the system is just the displacement of the center of the block. And because the block is rigid, every part of it moves with the same velocity, and the kinetic energy of the block is going to be the same as the kinetic energy of the system. Well, now I can use that equation for the change in the kinetic energy of the center of mass that disappointingly a few minutes ago wasn't what we needed because it wasn't the work on a system, but now it's useful to us. And since there's only one force here with an x component, it's the frictional force, that gives us a nice simple little expression. And the change in thermal energy is just the negative of that. Now be careful, that's misleading the way it's written, because it looks like it should be negative. But notice that that component of the frictional force is negative, and so the two negatives cancel out. And this expression is always positive. If you reverse the direction of the motion of the block, you should check that this still comes out positive. Students are often confused by the difference between a work by most forces and this change in thermal energy caused by a friction. There's actually a subtle difference that doesn't really show up well in the equations as I've written them here. So let's have a look at a specific situation. Here we have a block. It's initially sliding to the right. There is a tension due to some string and a kinetic friction acting on it. It stops, and because of the string pulling on it, it reverses direction and heads back the other way, at which point the friction is now pointing in the other direction. And let's compare the work done by this tension versus the change in thermal energy due to the friction that acts through this whole trip. So the first piece from the initial place to what I've called 1 here, the work is the x component of that tension, which is negative the magnitude of the tension, times delta x1, which is the x component of this displacement vector. Now, the thermal energy, we again have negative the x component of the friction, which is negative Fk times delta x1, and those negative signs cancel, and so we get a positive answer as promised. Now we look at the next part, from place 1 to place 2. Again, we have an x component of this tension that's negative Ft, and we're multiplying that by this x component of delta R2. And notice I've made it come back to its original place, so that is in fact negative delta x1, and the negative signs cancel. That'll be important in a moment. The thermal energy, again, we have negative, but now that component is positive since the friction is pointing the other way, times delta x2. Delta x2 is negative delta x1, and again, the negatives cancel, and this comes out positive as promised. Now look at the totals. The work totals up to 0 because we have two contributions that are exactly equal in size, but one is positive and one is negative. And notice we could have just taken the tension x component times the total displacement, as the equation says, and we would have got the right answer since the total displacement is 0. On the other hand, the thermal energies cannot add to 0 because they're both positive. And in fact, what we end up getting is the magnitude of the friction times this 2 delta x1, which is actually the distance, not the displacement, the distance that the block traveled. So here we have a real contrast that the work by the tension depends on the displacement, but the change in thermal energy depends on the distance, and we can actually rewrite our equation for change in thermal energy due to the friction force to be the magnitude of the friction force times the distance traveled, and now it's perhaps clearer that this will always be positive since both of these quantities are always positive.